Yo guys, what is good? It's Cam, aka Cameron, and this is gonna be the last reaction video with this wet hair that's like curtains. It looks kind of stupid on the camera, but actually doesn't look that too bad on the recording, so I don't know what it's gonna actually look like. No, we went to the wrong video. Okay, we gotta go back. We're gonna be learning, okay, educational Ron on right now. Nature has learned how to eat plastic. Now, I feel like this is doing. Let's like on principle, okay? Hit that like and subscribe button for me because we like the videos on principle. But I feel like this video, nature has learned to eat plastic, is gonna be like a like climate change isn't real type thing, like, you know. But we have no clue. Let's just listen, hear him out, see what he got to say, and make our own opinions, because that's all you can do. Remember, always trust your own opinion. Take the advice from the experts and then think if it makes sense or not.
Back in 2016, scientists at a recycling plant in Kyoto in Japan discovered a mysterious sludge that seemed to be engulfing a huge pile of plastic bottles that had been left in the yard outside the facility. It looked like the growth was actually feeding on the plastic itself, which was pretty weird because, as far as science was concerned, the stuff that these bottles was made from, a polymer called polyethylene terephthalate, or PET,
Drink some water.
was pretty much indestructible in nature. I imagine the thoughts racing through the scientists' minds were not unlike those that Alexander Fleming experienced when he came back to his lab after a summer holiday and noticed he'd rather clumsily left a petri dish open containing a bacterium he'd been working on called Staphylococcus. The exposed bacterium looked like it was being consumed by some sort of fungus, and Fleming realised that nature might just have gifted him something of great significance. In Fleming's case, of course, it turned out he'd accidentally discovered penicillin, which did prove to be really quite significant indeed.
Call me stupid, but people say when they go into the military, you gotta get your penicillin shot. Please let me know what that does. Okay, I'm actually gonna look it up. I need to look it up. My phone, I need to do that. But I just dropped it. It's already smashed. It's alright. But yeah, let me know what that actually does. I need to look it up. I don't know. I'm curious.
In the case of the Japanese scientists,
but if you know, just comment down below.
Plant, what they'd stumbled across was yet another example of nature's astonishing ability to overcome just about anything in the evolutionary struggle for life. The mystery sludge was in fact a microorganism containing a bacterium that had adapted to digest the plastic down into its constituent parts, using the carbon content as an energy source. The potential impact of this adaptation was not lost on the Japanese scientists, and because they were scientists, they decided to give this new bacterium the fantastically snappy name of Ideonella sakaiensis. Idiots. What was wrong with romper stomper plastic chomper?
It's not a scientific term, is it, you muppet?
I do like that name though. Romper Stomper Plastics Chomper.
Hello and welcome to Just Have a Think. Polyethylene terephthalate was regarded as a triumph of human ingenuity when DuPont started marking it as Mylar back in 1951. Up until then, plastic manufacturers had been struggling to find a material that could replace the heavy and expensive glass bottles that were used for drinks like colas and other sodas. They were already making plastic bottles, but if those bottles were filled with carbonated drinks and left on the shelf for more than a few days, the carbon dioxide gas molecules escaped through the polymer walls and the drinks went flat. So customers were complaining and sales were suffering. The structure of PET effectively reduces the gap in the polymer chain to a size that's smaller than a carbon dioxide molecule. The result was a lightweight, transparent, tough plastic bottle that kept fizzy drinks fizzy. The consequence of that was that sales doubled during the first few years after PET was introduced, and those sales numbers kept on going up and up. So much so that in 2016, 480 billion plastic bottles were produced globally. Only about 7% of them are actually recycled to perform the same function twice. About half of them get downcycled into something less valuable like fibres for clothing or flooring, and the rest end up in landfill or waterways. This chart from the Ellen MacArthur Foundation shows the growth in plastic production reaching more than 300 million metric tonnes by 2014. About 8 million tonnes of that plastic is now floating around in our oceans. Out there in the wild, as this graphic from the National Oceanic and Atmospheric Administration shows us, plastic bottles can hang around for as much as 450 years. And the plastic never goes away completely, of course. It just degrades into smaller and smaller microplastics that get ingested by sea life and then passed up the food chain to us humans, with all the potential health impacts that we hear so much about in the news these days. So you can probably see why our Japanese friends were feeling pretty motivated. On closer inspection of the new bacterium, the scientists found that it actually used specific enzymes to break down the two components of PET. Those two components are dimethyl terephthalate, or DMT, and ethylene glycol, both of which are originally derived from oil and combined by humans to make the very useful but also very problematic and virtually indestructible polymer chains. Once they're separated out though, both these compounds are harmless and potentially quite useful. But the Kyoto scientists knew from experience that there are all sorts of practical problems when you use microorganisms directly for industrial purposes. You have to let the bacteria grow to a usable size for a start, and you have very little control over whether the microorganisms thrive or die. So it's all a bit hit and miss, and big industrial manufacturing doesn't really do hit and miss. So the team drilled down and identified the gene in the bacteria's DNA that's responsible for the PET digesting enzyme. Then they reproduced that enzyme and did experiments that showed that just the enzyme on its own, without the rest of the bacterium, was enough to successfully break down the PET. And that was definitely one of those eureka moments. But as Thomas Edison once famously said, genius is 1% inspiration and 99% perspiration. And so it
The
proved
video
with
quality is
Ideonella
good, and I'm very
sakaiensis.
confused and
While the
lost.
rate of PET digestion was hundreds of times faster than the natural degradation of plastic in landfill or the ocean, it was still far too slow to cope with the incredible rate that new plastics are being churned out at all over the world. So the race was on to improve and strengthen the enzyme genetically so that it could digest far greater quantities of PET far more quickly. That research has been ongoing in several laboratories around the world ever since, with the goal of at least a 100-fold increase in the digestion rate. In 2019, the University of Portsmouth, here in the UK, established the Centre for Enzyme Innovation, or CEI. The Centre's Professor of Structural Biology, John McGeehan, recently presented a progress report on his team's research to a rapt audience at MTech in Hong Kong. McGeehan explained that over millions of years, nature has actually evolved its own natural polyester called cutin, which provides a waxy protective surface to plants. But over those evolutionary timelines, bacteria have also evolved that can eat through that cutin layer to get inside the plant and do all their destructive work. Using the now familiar lettering sequences of modern genetic engineering, the researchers were able to show that the PET-eating enzyme, called PETase, contained almost the exact same amino acid building blocks as the existing cutinase enzymes that nature had evolved over the eons. So now they knew the ancestry of the new enzyme, and they could see that it hadn't required a great leap of evolution for a bacterium that knows how to eat natural polyester to mutate into something that knows how to eat a synthetic one. What was remarkable though, says McGeehan, is the fact that this mutation only took 50 years or so to occur. And what they didn't yet know is how the new enzyme worked its magic. Using state-of-the-art technologies, the team purified and crystallized the enzyme. Then they fired X-rays at the crystals and recorded the refracted light in ultra-sensitive machines like synchrotrons and vacuum-sealed proton detectors to build up an extremely accurate three-dimensional model of the atomic structure of the PETase crystals, which looked like this. And when clever folks like Professor McGeehan are able to see three-dimensional atomic structures, they can start to understand how they work and hopefully how to make them work even better. When they compared the 3D structure of PETase to the 3D structure of cutinase, the team were able to identify the subtle changes in the PETase enzyme that allowed it to break down.
I have no clue what he's talking about at all whatsoever. I'm hoping someone understands and can explain it to me in the comments section. It doesn't really matter. All it cares is there's something that can eat plastic. Do you know what would be sick if they just put that chemical or fungus or whatever inside rubbish bins, genetically modified it to just speed the process up a ton, and then you just drop it in it, it just incinerates everything? That would be sick.
Down PET. Cutinase enzymes break the natural...
Oh, like hotels and like big buildings, how they have the rubbish chutes that you like put it down. Imagine they just have like a giant just place just in the bottom with like a bunch of this fungus or chemical or whatever it is, and that just eats everything away. How sick would that be?
bonds with chemical jaws at this active point where the gap is just less than 3/10 billionth of a metre, or 0.3 nanometres.
The agasm or angstrom is a metric unit of length equal to 10 to the power of negative 10 m. That is 1/10 billionth of a meter, 0.1 nanometers, or 100 pictometers. Symbol is A, and the letter of the Swedish alphabet. Very interesting. So it's a very, very small, like that. Probably smaller.
What the research team found was that with only a single amino acid change in its structure, the PETase enzyme had changed the shape of the jaws at its active point to make the gap almost 3 times wider. And that change was all it took to enable the new PETase enzyme to accommodate a man-made aromatic polymer like PET. The challenge then was to apply some sort of reverse engineering to see where the process could be turbocharged to meet the needs of our global plastic waste problem. First of all, they looked at the surface of a plastic bottle under an electron microscope over 96 hours while it was being digested by the PETase enzyme. As the polymer structure broke down, the scientists could identify the basic building blocks of DMT and ethylene glycol accumulating around the edges of the digestion area. Then, with some advanced computer modelling, courtesy of the Woodcock Group at the University of South Florida, they produced an accurate image of how the enzyme cuts the bond in the PET polymer chain to release the individual monomers. Then came the reverse engineering bit. The team tried to manipulate the enzyme to turn it back into cutinase. The idea was that by precisely controlling the steps in that laboratory process, they could perhaps determine what they could do going in the other direction to mutate the PETase into something more effective. But the experiment failed to produce a cutinase enzyme. Instead, by sheer chance, what it actually produced was a vastly improved PETase enzyme. These green bars represent the relative sizes of the crystalline structures of the PETase enzyme and the accidentally discovered new enzyme. You can see that there's a huge increase, which in turn leads to a much faster rate of digestion. The CEI team don't profess to have solved the world's plastic problems just yet, but what they have shown is that it's possible to engineer a more effective enzyme just by making very small changes to its DNA. And they suggest that it's entirely possible that nature may have produced other enzymes that have found ways to digest the other plastics that we've created since the middle of the 20th century. We just need to do the slightly unpleasant work of rooting around in plastic recycling dumps to try and find them. The future of this research looks very promising indeed, though. Professor McGeehan is confident that they can engineer faster and faster enzymes, and he outlines what he hopes the R&D roadmap will look like. In an ideal world, this sort of research would be regarded as essential to species survival and would be co-funded by every government on Earth as some sort of priority. In the real world of market-driven capitalism, it will most likely be commercial investment that ultimately provides the key to producing effective enzymes at a large enough scale to make a really positive impact on plastic recycling. But the company with the long-term vision to recognise the value of this work will also get themselves the added bonus of 2 very useful and very marketable byproducts. Professor Anne Meyer, who heads up a separate PETase research group based at the Technical University of Denmark, points out that ethylene glycol can be used directly in antifreeze, which is in very high demand all around the world and is currently manufactured from non-renewable materials. It's also possible to produce a hybrid material from paper and recycled plastic components that has the right strength properties to be used as a carrier bag, but can also be fully recycled or biologically degraded. And the really great thing for our dear investors is that there's very little chance they're going to run out of raw material anytime soon. Let us know your thoughts in the comment section below. That's it for this week, though. A massive thank you, as always, to the...
That's crazy. So pretty much they found something that can dissolve plastic and you get paper and bags and stuff from it. Very, very cool. Yeah, that's all I understand pretty much. Let me know, comment down below how much you understand. Let me know if I got some geniuses watching or something like that. I suck at science, like literally. I don't do any sciences at school. Dropped all of them because I hate science. But that was somewhat interesting, even though I have no clue what's going on. Could have read the title, pretty much understood the same thing. But it doesn't seem like it's pseudoscience. He seems like he's talking about something legit. That's very, very interesting. Let me know if I'm speaking facts or not, or if it is more pseudoscience that's actually completely unproven. Everything he was doing is just made up for entertainment purposes. Either way, guys, hit that like and subscribe button. I know it's a bit of a different video, but we just react to anything on this channel. Oh, I saw that. I saw start streaming. I thought I wasn't recording. Either way, guys, that's the end of the video. I hope you guys enjoyed it. If you did, please hit that like and subscribe button. I'm out. See ya.